The history of discovering planets outside our solar system was really dominated by these hot planets. And that's just because of the fact they're easier to find. When the very first methods came online, these were primarily the Doppler spectroscopy method, looking for wobbling stars, and also the transit method. And these two both have a really strong bias towards finding these hot planets. Now, hot planets are interesting. The chemistry in their atmosphere is fascinating. It's very alien. An example of one that's particularly close to my heart is TRACE-2b, whose atmosphere is so dark, it's less reflective than coal. And so they have really bizarre photometric properties, yet at the same time, they resemble nothing like our own home. And so it said there's two types of astrophysicists. The astrophysicists who care about how the universe works. They want to understand the mechanics of the machinery of this universe. Why did the Big Bang happen? Why is the universe expanding? How are galaxies formed? And there's another type of astrophysicist which perhaps speaks to me a little bit more. It whispers into your ear, and that is, why are we here? Are we alone? Are there others out there? And ultimately, along this journey, the hot planets aren't going to get us there. When we're looking for life in the universe, it seems to make perfect sense that there should be planets like our own out there, maybe even moons like our own planet around gas giants that could be habitable. And so my research has been driven by trying to find these more terraqueous globes that might resemble our own planet.
So they're the ones that lurk more in the shadows in terms of how difficult it is to detect.
They're much harder. They're harder for several reasons. The method we primarily use is the transit method. So this is really eclipses. As the planet passes in front of the star, it blocks out some starlight. The problem with that is that not all planets pass in front of their star. They have to be aligned correctly from your line of sight. And so the further away the planet is from the star, the cooler it is, the less likely it is that you're going to get that geometric alignment. So whereas a hot Jupiter, about 1% of hot Jupiters will transit in front of their star, only about 0.5%, maybe even 0.25% of Earth-like planets will have the right geometry to transit. And so that makes it much, much harder for us.
What's the connection between temperature of the planet and geometric alignment, probability of geometric alignment?
There's not a direct connection, but they're connected via an intermediate parameter, which is their separation from the star. So the planet will be cooler if it's further away from the star, which in turn means that the probability of getting that alignment correct is going to be less. On top of that, they also transit their star less frequently. So if you go to the telescope and you wanted to discover a hot Jupiter, you could probably do it in a week or so, because the orbital periods of order of 1, 2, 3 days. So you can actually get the full orbit 2 or 3 times over. Whereas if you wanted to detect an Earth-like planet, you have to observe that star for 3, 4 years. And that's actually one of the problems with Kepler. Kepler was this very successful mission that NASA launched over a decade ago now, I think. And it discovered thousands of planets. It's still the dominant source of exoplanets that we know about. But unfortunately, it didn't last as long as we would have liked it to. It died after about 4.35 years, I think it was. And so for an Earth-like planet, that's just enough to catch 4 transits. And 4 transits was kind of seen as the minimum. But of course, the more transits you see, the easier it is to detect it, because you build up signal to noise. If you see the same thing tick, 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 the more ticks you get, the easier it is to find it. And so it was really a shame that Kepler was just at the limit of where we were expecting it to start to see Earth-like planets. And in fact, it really found zero planets that are around stars like the sun, that orbit similar to the Earth around the sun, and could potentially be similar to our own planet in terms of its composition. And so it's a great shame, but that's why it gives astronomers more to do in the future.
Just to clarify, the transit method is our primary way of detecting these things. And what it is when the object occludes the source of light just a tiny bit, a few pixels. And from that, we can infer something about its mass and size and distance and geometry, all of that. That's like trying to tell what, at a party, you can't see anything about a person, but you can just see by the way they occlude others. So this is the method. But this is super far away. How many pixels of information do we have? Basically, how high resolution is the signal that we can get about these occlusions?
You're right in your description. I think just to build upon that a little bit more, it might be almost like your vision is completely blurry. Like you have an extreme eye prescription, and so you can't resolve anything. Everything's just blurs. But you can tell that something was there because it just got fainter for a short amount of time. Someone passed in front of a light.
Yeah.
And so that light in your eyes would just dim for a short moment. Now, the reason we have that problem with blurriness or resolution is just because the stars are so far away. I mean, the closest stars are 4 light years away, but most of the stars Kepler looked at were thousands of light years away. And so there's absolutely no chance that the telescope can physically resolve the star, or even the separation between the planet and the star is too small, especially for a telescope like Kepler. It's only a meter across. In principle, you can make those detections, but you need a different kind of telescope. We call that direct imaging. And direct imaging is a very exciting, distinct way of detecting planets. But it, as you can imagine, is going to be far easier to detect planets which are really far away from their star to do that, because that's going to make that separation really big. And then you also want the star to be really close to us, so the nearest stars. Not only that, but you would prefer that planet to be really hot, because the hotter it is, the brighter it is. And so that tends to bias direct imaging towards planets which are in the process of forming. Mm-hmm. So things which have just formed, the planet's still got all of its primordial heat embedded within it, and it's glowing. We can see those quite easily. But for the planets more like the Earth, of course, they've cooled down, and so we can't see that. The light is pitiful compared to a newly formed planet. We would like to get there with direct imaging. That's the dream, is to have the pale blue dot, an actual photograph of it, maybe even just a 1 pixel photograph of it. But for now, the entire solar system is 1 pixel, certainly with the transit method, most other telescopes. And so all you can do is see where that 1 pixel, which contains potentially dozens of planets and the star, maybe even multiple stars, dims for a short amount of time.
It dims just a little bit, and from that you can infer something.
Yeah, I mean, it's like being a detective in the scene, right? It's indirect clues of the existence of the planet.
It's amazing that humans can do that. We're just looking out in these immense distances and looking, if there's alien civilizations out there, like let's say one exactly like our own, we're like, would we even be able to see an Earth that passes in the way of its sun and slightly dims? And that's the only sign we have of that alien human-like civilization out there, is it's just a little bit of a dimming.
Yeah. I mean, it depends on the type of star we're talking about. If it is a star truly like the sun, the dip that causes is 84 parts per million. I mean, it's like the same as like a firefly flying in front of like a giant floodlight at a stadium or something. That's the kind of the brightness contrast that you're trying to compare to. So it's extremely difficult detection. And in the very, very best cases, we can get down to that. But as I said, we don't really have any true Earth analogs that have been in the exoplanet candidate yet. Unless you relax that definition, you say, doesn't have to be a star just like the sun. It could be a star that's smaller than the sun. It could be these orange dwarfs or even the red dwarf stars. And the fact those stars are smaller means that for the same size planet passing in front of it, more light is blocked out. And so a very exciting system, for example, is Trappist-1, which has 7 planets which are smaller than the Earth. And those are quite easily detectable, not with a space-based telescope, but even from the ground. And that's just because the star is so much smaller that the relative increase in or decrease in brightness is enhanced significantly because that smaller size. So TRAPPIST-1e, it's a planet which is in the right distance for liquid water. It has a slightly smaller size than the Earth. It's about 90% the size of the Earth, about 80% the mass. And it's one of the top targets right now for potentially having life. And yet it raises many questions about what would that environment be like. This is a star which is 1/8 the mass of the sun. It's stars like that take a long time to come off their adolescence. Mm-hmm. When stars first form, like the sun, it takes them maybe 10, 100 million years to sort of settle into their main sequence lifetime. But for stars like these late M-dwarfs, as we call them, they can take up to 1 billion years or more to calm down. And during that period, they're producing huge amounts of X-rays, ultraviolet radiation that could potentially rip off the entire atmosphere. It may desiccate the planets in the system. And so even if water arrived by comets or something, it may have lost all that water due to this prolonged period of high activity. So we have lots of open-ended questions about these M-dwarf planets, but they are the most accessible. And so in the near term, if we detect anything in terms of biosignatures, it's going to be for one of these red dwarf stars. It's not going to be a true Earth twin, as we would recognize it as having a yellow star.
Well, let me ask you, I mean, there's a million ways to ask this question. I'm sure I'll ask it about habitable worlds. Let's just go to our own solar system. What can we learn about the planets and moons in our solar system that might contain life, whether it's Mars or some of the moons of Jupiter and Saturn? What kind of characteristics, because you said it might not need to be Earth-like, what kind of characteristics might we be looking for?
When we look for life, it's hard to define even what life is, but we can maybe do a better job in defining the sorts of things that life does. And that provides some aspects to some avenue for looking for them. Classically, conventionally, I think we thought the way to look for life was to look for oxygen. Oxygen is a byproduct of photosynthesis on this planet. We didn't always have it. Certainly, if you go back to the Archean period, there was, you have this period called the Great Oxidation Event, where the Earth floods with oxygen for the first time and starts to saturate the oceans and then into the atmosphere. And so that oxygen, if we detected it on another planet, whether it be Mars, Venus, or an exoplanet, whatever it is, that was long thought to be evidence for something doing photosynthesis. Because if you took away all the plant life on the Earth, the oxygen wouldn't just hang around here. It's a highly reactive molecule. It would oxidize things. And so within about 1 million years, you would probably lose all the oxygen on planet Earth. So that was conventionally how we thought we could look for life. And then we started to realize that it's not so simple, because there might be other things that life does apart from photosynthesis. Certainly the vast majority of the Earth's history had no oxygen, and yet there was living things on it. So that doesn't seem like a complete test. And secondly, could there be other things that produce oxygen besides from life? A growing concern has been these false positives in biosignature work. And so one example of that would be photolysis that happens in the atmosphere. When ultraviolet light hits the upper atmosphere, it can break up water vapor. The hydrogen splits off to the oxygen. The hydrogen is a much lighter atomic species, and so it can actually escape certainly planets like the Earth's gravity. That's why we don't have any hydrogen or very little helium. And so that leaves you with the oxygen, which then oxidizes the surface. And so there could be a residual oxygen signature just due to this photolysis process. So we've been trying to generalize, and certainly in recent years, there's been other suggestions of things we could look for in the solar system and beyond. Nitrous oxide, basically laughing gas, is a product of microbes. That's something that we're starting to get more interest in looking for. Methane gas in combination with other gases can be an important biosignature. Phosphine as well, and phosphine is particularly relevant to the solar system because there was a lot of interest for Venus recently. You may have heard that there was a claim of a biosignature in Venus's atmosphere. I think it was like 2 years ago now. And the judge and jury are still out on that. There was a very provocative claim and signature of a phosphine-like spectral absorption. But it could have also have been some other molecule, in particular sulfur dioxide, which is not a biosignature.
So this is a detection of a gas in the atmosphere of Venus. And it might be controversial on several dimensions. So one, how to interpret that. 2, is this the right gas? And 3, is this even the right detection? Is there an error in the detection?
Yeah. I mean, how much do we believe the detection in the first place? If you do believe it, does that necessarily mean there's life there? And what gives? How can you have life in Venus's atmosphere in the first place? Because that's been seen as like a hellhole place for imagining life. But I guess the counter to that has been that, okay, yes, the surface is a horrendous place to imagine life thriving. But as you go up in altitude, the very dense atmosphere means that there is a cloud layer where the temperature and the pressure become actually fairly similar to the surface of the Earth. And so it may be there are microbes stirring around in the clouds which are producing phosphine. Mm-hmm. At the moment, this is fascinating. It's got a lot of us reinvigorated about the prospects of going back to Venus and doing another mission there. In fact, there's now 2 NASA missions, Veritas and Da Vinci, which are going to be going back and before 2030 or the 2030s. And then we have a European mission, I think, that's slated now, and even a Chinese mission might be coming along the way as well. So we might have multiple missions going to Venus, which has long been overlooked. I mean, apart from the Soviets, there really has been very little in the way of exploration of Venus, certainly as compared to Mars. Mars has enjoyed most of the activity from NASA's rovers and surveys. And Mars is certainly fascinating. There's, this signature of methane that has been seen there before. Again, the discussion is whether that methane is a product of biology, which is possible. Certainly that happens on the Earth, or whether it's some geological process that we are yet to fully understand. It could be, for example, a reservoir of methane that's trapped under the surface and is leaking out seasonally.
So the nice thing about Venus is if there's a giant living civilization there, it'll be airborne, so you can just fly through and collect samples.
Yeah.
With Mars and moons of Saturn and Jupiter, you're going to have to dig under to find the civilizations,
right.
dead or living.
Right. And so, maybe it's easier then for Venus, because certainly you can imagine just a balloon floating through the atmosphere, or a drone or something that would have the capability of just scooping up and sampling. To dig under the surface of Mars is maybe feasible-ish, with, especially with something like Starship that could launch, a huge digger basically to the surface, and you could just excavate away at the surface. But for something like Europa, we really are still unclear about how thick the ice layer is, how you would melt through that huge, thick layer to get to the ocean, and then potentially also discussions about contamination. The problem with looking for life in the solar system, which is different from looking for life with exoplanets, is that you always run the risk of, especially if you visit there, of introducing the life yourself, right? It's very difficult to completely exterminate every single microbe and spore on the surface of your rover or the surface of your lander. And so there's always a risk of introducing something. I mean, to some extent, there is continuous exchange of material between these planets naturally on top of that as well. And now we're sort of accelerating that process to some degree. And so if you dig into Europa's surface, which probably is completely pristine, it's very unlikely there has been much exchange with the outside world for its subsurface ocean, you are, for the first time, potentially introducing bacterial spores into that environment that may compete or may introduce spurious signatures for the life you're looking for. And so it's almost an ethical question as to how to proceed with looking for life on those subsurface oceans. And I don't think one we've really have a good resolution for at this point.
Ethical. So you mean ethical in terms of concern for for preserving life elsewhere? Not
right.
Not to murder it, as opposed to the scientific one?
I mean, we always worry about a space virus, right? Coming here, or some kind of external source, and we would be the source of that potential contamination.
Or the other direction.
Yeah.
I mean, the whatever survives in such harsh conditions might be pretty good at surviving in all conditions. It might be a little bit more resilient and robust. So it might actually take a ride on us back home.
Possibly. I mean, I'm sure that some people would be concerned about that. I think we would hopefully have some containment procedures as if we did sample return. Or you mean you don't even really need a sample return. These days you can pretty much send it like a little micro laboratory to the planet to do all the experiments in situ, and then just send them back to your planet, the data. And so I don't think it's necessary that, especially for a case like that where you might have contamination concerns, that you have to bring samples back. Although probably if you brought back European sushi, it would probably sell for quite a bit with the billionaires in New York City.
Sushi, yeah. I would love, from an engineering perspective, just to see all the different candidates and designs for like the scooper for Venus and the scooper for Europa and Mars. I haven't really looked deeply into how they actually, like the actual engineering of collecting the samples, because that's the engineering of that is probably essential for not either destroying life or polluting it with our own microbes and so on. So that's like an interesting engineering challenge. I usually, for rovers and stuff, focus on the sort of the mobility aspect of it, on the robotics, the perception, and the movement, and the planning and the control. But there's probably the scooper is probably where the action is. The microscopic sample collection. So basically, you have to first clean your vehicle, make sure it doesn't have any Earth-like things on it, and then you have to put it into some kind of thing that's perfectly sealed from the environment. So if we bring it back or we analyze it, it's not going to bring anything else external in. Yeah, I don't know. That'd be an interesting engineering design there.
Yeah, I mean, Curiosity has been leaving these little pods on the surface quite recently. There's some neat photos you can find online, and they kind of look like lightsaber hilts. Which so, to me, I think I tweeted something like, this weapon is your life. Like, don't lose it, Curiosity, because it's just dumping these little vials everywhere, and it is scooping up these things. And the intention is that in the future, there will be a sample return mission that will come and pick these up. Mm-hmm. But the engineering behind those things is so impressive. The thing that blows me away the most has been the landings. Especially, I'm training to be a pilot at the moment, so that's the sort of, watching landings has become like my pet hobby on YouTube at the moment, and how not to do it, how to do it with different levels of conditions and things. But with the, when you think about landing on Mars, just the light travel time effect means that there's no possibility of a human controlling that descent. Mm-hmm. And so you have to put all of your faith and your trust in the computer code or the AI or whatever it is that you've put on board that thing to make the correct descent. And so there's this famous period called 7 minutes of hell, where you're basically waiting for that light travel time to come back to know whether your vehicle successfully landed on the surface or not. And during that period, in your mind simultaneously that it is doing these multi-stages of deploying its parachute, deploying the crane, activating its jets to come down and controlling its descent to the surface. And then the crane has to fly away so it doesn't accidentally hit the rover. And so there's a series of multi-stage points where any of them go wrong, the whole mission could go awry. And so the fact that we are fairly consistently able to build these machines that can do this autonomously is, to me, one of the most impressive acts of engineering that NASA have achieved.